So, our third problem is, so we will have a circuit and the circuit in the figure has nominal gain of 10, that is 1 plus R 1 by R 2 equal to 10, and also it has been given that the op amp is not ideal. I will go this point in more detail while discussing the solution. There is the op amp is not ideal. So, the gain obtainable will always be less than the ideal, and we have been given the transfer function of the op amp is A naught by 1 plus S by omega p, and we know that A 0 is the DC gain of the op amp and omega p is the pole frequency. So, the op amp is plus, this is minus, this is R 2, R 1. The input that we have given here, this V I, the input is actually like this. Is a simple pulse input, uniform amplitude, this is 1 volt, this also is, sorry, this is T scale, this is 1 microsecond and this is 1 volt, this is 1 volt, and here also it is repeating, and the output is, it is going like this, it is touching this, then it is decaying and then it is going like this. Now, the problem is, the first portion is only for this part assume that the output gets settled completely and input can be thought of as DC value of 1 volt. So, what we have to find out? We have to find out, determine the minimum value of A 0 such that the V out is 99% of the expected output value in case of the op amp is ideal. Now, look one by one. So, what we have to find out? So, solution for part A. So, the circuit given is a simple op amp circuit, this is plus, this is minus, here we are giving V I, here it is R 2, it is R 1, it is V out. Now, assume that the output gets settled completely. So, when the input is being applied is like this, and we are telling output is get settled, which means that A naught for this problem, A naught actually is a constant quantity, it is not function of S, because we are considering in the steady state conditions. where the output gets settled, means output we are getting a DC. So, we can write that VO by Vi equal to A0 plus 1 by A0 beta. Now, A0, as we have already discussed, it is a constant quantity. So, now beta is what? For this circuit, beta is the feedback factor. So, feedback factor means how much portion of the output voltage is being sampled and is fed back to our input. So, beta is the amount of feedback. Generally, beta we define Vf equal to beta V0, and in our case beta is R2 is the potentially dividing the output voltage and it is feeding back to the input. So, beta is from the potential divider, one can find out that beta is R2 by R1 plus R2. Now, in the problem we have already know that 1 by R1 plus R2 is equal to 10, this is given. So, R2 plus R1 by R2 equal to 10. So, R2 by R1 plus R2, it is coming out to be 0.1. Then from this one, VO by Vi equal to A0 by 1 plus 0.1 A0, this beta value we have put, which is A0. Now, let us see the problem. So, after this, determine the minimum value of A0 such that the Vout is, this Vout is 99% of the expected output value in case of the op amp is ideal. Now, let us suppose if the op amp is ideal, then what will be happen? If the op amp is ideal, then for ideal op amp, VO by Vi is A by 1 plus A beta. For ideal op amp, the open loop gain is infinite. So, 1 by A plus beta. Now, for ideal case, as A tending to infinity, we can write that it is coming out 1 by beta. So, the VO by Vi for ideal op amp, VO by Vi is coming out the same value, which is the open loop gain given in the problem, that is 10. Now, we want that our minimum value of A0 such that, determine the minimum value of A0 such that the Vout is 99% of the expected output value in case of the op amp is ideal. So, it will be this tens 99% A0 1 plus 0.1 into A0. So, if we solve this one, we will get that A0 will come 990. This is our minimum value of A0, for which the output will be the 99% of the ideal op amp's output value. Now, let us have a look at the second part of the problem. This is the problem third only, but this is the second part. For this part, assume that the input is a unit step from 0 to 1 microsecond. Find the expression of Vout t. For the same op amp, now what is the problem? For the same op amp, now at the input we are having a unit step from 0 to 1 microsecond. and the AS, the same AS that I am writing, A0 by 1 plus S by omega p. So, what will be its solution? So, we have to find out actually the expression in time domain at the V output when the excitation is an unit step and the step is varying from 0 to 1 microsecond. So, VO by VI AS plus, this case the output is not settling. So, we will assume that the AS is A naught by 1 plus S by omega p divided by 1 plus A naught beta 1 plus S by omega p. So, VOS by V in S, if we simplify this one, it is going to come A naught omega p by into 1 plus A naught beta plus S. So, VOS. So, now this portion we can separate it in partial fraction and we can write VOS equal to V in S A naught by 1 plus A naught beta S minus A naught by 1 plus A naught beta omega p plus A naught beta plus S. Now, we have applied what? We have applied an unit step. So, for an unit step function V in S, for unit step ut will be Laplacian of this one will be 1 by S. Actually, this is already multiplied. So, I have V in S is already multiplied and this 1 by S is coming because of this after partial separation. So, we will calculate 1 plus A naught beta ut minus, this is simply inverse Laplacian time domain we are taking, omega p 1 plus A naught beta t ut. So, this is our final output in time domain. When the signal at the input is an unit step function and it is varying from 1 microsecond a step, at that time the output it is in time domain will look like this. You can see that it is an unit step, from there decaying magnitude on the exponential function which is gradually decaying. Now, let us have a look at the third part of the same problem. If the V out t should get settled to 99.99% of the final value in 1 microsecond duration, what should be the pole frequency omega p? Use the value of A0 obtained at part A. So, what actually we have to see, if the V out that we have found out in our previous expressions, this is this one. should get settled to 99% of the final value in 1 microsecond. So, the final value of this one means, if this case V out t, if t tends to infinity here, we will get that the V out t in the previous case, if t tending to infinity, V O t, it is coming out. So, this t tending to infinity means this portion will go, e to the power minus infinity is 0. So, final value is going to come a naught by 1 plus a naught beta, and we have 99% of the final value. So, of this 99%, so it will be looking like 0.99. So, 0.9999 a naught by 1 plus a naught beta is the final output voltage that is desired, and that we have to achieve at t equal to microsecond, t equal to 1 microsecond, and we have to find out that what is the corresponding pole frequency. So, we know that the output is this one 0.999 of a naught by 1 plus a naught beta, and our beta value, it is given in the problem. A naught is actually, they are telling that use the value of a naught obtained in part A. So, a naught is also known to us. So, we have to just find out what is the value of omega p. So, it is 1 minus ut is 1 minus omega p, and if you can recollect, a naught we have calculated in our first problem, it is 990. So, it is 990 and beta is 0.1, that is already given, t is 1 microsecond, so it is coming t to 10 to the power minus 6 1 microsecond. So, I am writing here, because these values we have taken from our given problem set, and one problem and one value we have determined, that value we are using. So, a naught it is 990 and is beta is 0.1. So, let me take another sheet. So, let me write it. So, this is going to come 100 into 10 to the power minus 6, because this is 990 into 0.1. So, it will come 1 plus 99 100 10 to the power minus 6. So, this and this will go out. So, we will have 0 point this one 1 minus e to the power minus omega p into 10 to the power minus 4. So, all values are known, only omega p we have to find out. So, e to the power minus of omega p 10 to the power minus 4, 1 minus of 0.999, if we take the ln on both side, it will come ultimately omega p equal to 9.21 into 10 to the power minus 4. So, it is 9.21 into 10 to the power 4 rad per second, or it is 92.1 kilo rad per second. So, this is our pole frequency. So, that was the last part of the problem. So, what we have seen? We have seen that if any op amp problem is given, we have been supplied only the open loop transfer function of this op amp, that is A s, and we know that what is the input applied, and if the input is applied to the system known, then we can easily find out the output by using the relation V o by V I a by 1 plus a beta, and by using the Laplacian operator we can find out what is the time domain expression after applying that input. And if once we are getting the time domain expression, just we can play with the values given and we can get any unknowns that is required to be find out. So, suppose in present case we have to find out the pole frequency. So, we have easily find out that what the pole frequency is coming. So, today I have covered 3 problems. The first problem actually is one was in MOSFET's internal circuit, and in that MOSFET internal circuit given, just we have to see the output voltage, and from that we have calculated the gain, and from that gain we can easily see what will be the pole frequency and zero frequency. As for the first problem, just we have stopped how to calculate the V o by V I, and in the second problem it is little bit a trickier one. We have taken a op amp where the feedback is given by an RC or a combination of RC or any whatever combinations, and the solving for the problem is the same way. We have to find out the V o by V I, and then we have to take it in the Laplacian domain or the function of omega. Then by splitting up at low frequency or at the high frequency, we have to just can calculate, or we can simplify the results, that what will be the gain at the lower frequency, what may be the gain at the higher frequency, and from the same expression eventually we can calculate the omega p and omega z, that is the pole frequency and the zero frequency. And with these informations in hand, we can easily draw the board plot of any system or circuit that is given in the figure. So, if you see that these problems that we have taken, these problems are not a simpler one like the normal nodal analysis or KCL or KVL analysis that we have come across in any general electrical circuits book. This is the one which is related to some concepts that we may have come across in the exams, and from how to proceed that one for any given circuit, that is being described here. And the same way that we have described these questions or these problems for any circuit given, the approach should be the same. And for the third problem, we have just found out in the time domain expression, and we have also seen that if the expressions come out in the time domain, then how to find out the final value at t tends to infinity, and how to calculate the omega p's and omega z's. In the next tutorial, we will see some problems actually on gain margin and phase margin related to the op amps, and we will discuss some problems on filters like Butterworth filter and Chebyshev filter. And also we will try to see that how the step by step procedures, how these filters can be designed, so that at any point of time if you are given any filter design exercise, we can do that with the experience that we will learn in the next tutorials. Thank you.